In the modern air war, the enemy doesn't need to outfly you. They just need to detect you early enough to cue the rest of the kill system. A fighter can be fast and agile, but if it's visible first, it's already late. That's the environment the F-35 was built for. Not a sky with empty space and clean dogfights, but a battle space layered with radars, electronic surveillance, data links, and long-range weapons. The F-35 Lightning II is best understood as a packaging problem solved with brutal priorities. The goal wasn't to build the perfect airshow aircraft. The goal was to create a survivable strike and sensor platform that can operate inside contested airspace, collect high-quality information, and deliver weapons while remaining difficult to track. That means the airframe is not just shaped for stealth. It is engineered around stealth as a first-class design constraint. Geometry, edges, surface alignment, inlet design, and the discipline of keeping the aircraft's exterior clean from the standpoint of radar and signature management. Stealth is not invisibility, it's a time advantage. It forces the enemy to work harder to detect you, to classify you, and to maintain a stable track. In a modern engagement, that time advantage is everything. It buys you the ability to move closer, to sense more accurately, to choose when to reveal yourself, and to take the shot before the enemy can confidently respond. One of the most visible design choices is internal weapon carriage. External stores are a signature problem. They add reflections, change airflow, increase drag, and create strong radar cues. The F-35's internal bays let it carry weapons while preserving a lower observable profile. That's not a cosmetic trick, it's mission design. When you can carry meaningful weapons internally, you can operate in a higher threat environment earlier in a conflict, when defenses are still intact. When the threat is reduced or the mission changes, the aircraft can also carry external stores, trading signature for payload. Because real air wars demand flexibility, not purity. Under the skin, another constraint dominates: volume. Volume is fuel, cooling, power generation capacity, avionics space, and growth margin. Modern sensors and computing generate heat, and heat management is an engineering battlefield of its own. The F-35 is shaped not just for aerodynamic performance, but to host an ecosystem: radar, electro-optical systems, electronic warfare hardware, mission computers, power management, and the interfaces that let those subsystems work as one. The engine is the brute force that makes this packaging possible. A single-engine design reduces complexity and weight compared to twin engines, but it demands confidence in propulsion reliability and maintenance discipline. The engine has to provide enough thrust to carry internal fuel, internal weapons, and heavy mission systems, while supporting variants that have very different launch and recovery constraints. And those variants are not a footnote. They are the reason the F-35 program is so ambitious and why it can look like 3 aircraft wearing one name. The F-35A is the conventional takeoff and landing variant. It's the baseline model optimized for standard runways and the broadest set of Air Force missions. It is typically the lightest of the 3 in structural terms, because it doesn't need the reinforcements and deck handling adaptations of carrier life. And it doesn't carry the STOVL lift hardware of the B, that translates into efficiency advantages and handling characteristics aligned with conventional Air Force operations. The F-35B is a short takeoff and vertical landing variant. This is the version built for forces that need flexible basing, short strips, austere locations, and amphibious ships. But STOVL capability doesn't come for free. It requires specialized lift architecture and structural decisions that influence internal volume, weight distribution, and thermal stresses. The B exists because basing is a strategic vulnerability. If access to long runways is threatened or politically uncertain, aircraft that can operate from more flexible locations expand operational options. In real conflicts, basing constraints can decide what air power can even show up and when. The F-35C is the carrier variant. Carrier aviation is a punishment environment: catapult launches, arrested landings, salt corrosion, deck handling, and long-range maritime mission profiles. The C is built with a larger wing for low-speed carrier approach performance, stronger landing gear, and structural reinforcements for repeated deck cycles. That wing is not just a shape, it's a mission statement. It's about endurance, bring-back capability, and carrier recovery constraints that are non-negotiable physics. A clean way to understand the F-35 family is to think in trade-offs. The A emphasizes conventional efficiency. The B buys basing flexibility at structural and packaging cost. The C buys carrier suitability with reinforced structures and aerodynamic changes that support deck operations. But across all of them, the philosophy remains consistent. Survive, sense, strike, and do it in a way that fits into modern coalition warfare. Now let's talk about the part people obsess over: performance. The F-35 is not a pure air superiority dogfighter in the classic sense. It doesn't exist to chase speed records. It exists to deliver combat power in the threat environment that defines the 21st century: dense sensing, dense networking, long-range engagement timelines. Performance still matters. Acceleration, energy management, climb, and agility are always relevant. But the program's central bet is that information advantage and survivability can dominate the engagement long before a turning fight begins. The aircraft also has a very specific advantage that rarely gets explained well. It is designed to carry a high-quality sensor and compute suite without being forced into external pods as the primary path. Pods are useful, but they add drag, signature, and integration complexity. The F-35's idea is that the sensors are part of the aircraft's core identity, not optional accessories. That means the airframe isn't just delivering weapons, it is delivering awareness and decision speed. In a modern battle space, survivability is not a single feature. It is a stack. It includes reduced observability. It includes threat awareness. It includes electronic warfare. It includes data sharing. It includes the ability to act first. The F-35's airframe is the foundation of that stack. It is the shell that lets the rest of the system do its job, closer, longer, and with more confidence. That's why the aircraft is so strategically valuable. It isn't merely a platform that fires missiles. It's a platform designed to enter the most contested parts of the map and remain useful there. When an aircraft can survive where others cannot, it becomes the one that shapes the opening phase of a fight. And the opening phase is where modern wars are often decided. The sensors, the fusion, and the kill web effect. The F-35's real power is not a single sensor. It's what happens when many sensors stop behaving like separate instruments and start behaving like a single brain. In older fighters, sensors often live in separate worlds. Radar on one page, targeting pod on another, electronic warning on another, off-board tracks somewhere else. The pilot becomes the integration bus. That works until the workload spikes, then the pilot becomes the bottleneck. The F-35 is built on a different assumption. The aircraft should do the integration continuously and automatically, so the pilot can spend more time deciding and less time stitching reality together. That assumption is sensor fusion, and it's not a buzzword when it's done right. It's the difference between being overwhelmed and being decisive. The aircraft's sensor stack is designed to cover multiple phenomenologies. Radar gives one kind of truth: range, velocity, track stability in many conditions. Infrared gives another: passive detection and imagery cues that don't require emitting like a radar. Electro-optical targeting adds identification and precision tracking. Electronic warfare sensing adds awareness of what's happening in the electromagnetic environment. Who is searching, who is tracking, who is trying to engage, and what kind of system is lighting up the spectrum. Those inputs are not always consistent. The environment is full of ambiguity. A radar return can be a real target or interference. An infrared cue can be a genuine track or a confusing thermal source. Electronic warnings can overlap. Off-board tracks can be delayed or degraded. The art is not collecting more signals. It's assigning confidence and meaning. That's the central promise of fusion. Merge sensor inputs, compare them, resolve conflicts, and present the pilot with a coherent picture that is more reliable than any single sensor alone. It's also a time weapon. The faster the aircraft can build certainty, the faster it can assign priorities, and the faster it can act. But fusion alone is not enough. The pilot has to receive that fused picture in a way that reduces cognitive load rather than creating a new kind of confusion. That's why the F-35's cockpit and helmet concept matters. The pilot is not meant to be an operator of separate sensors. The pilot is meant to be the decision maker on top of an integrated system. In practical terms, that means the aircraft is designed to keep the pilot oriented. What matters, where it is, how confident the system is, what the threats are, and what options exist. When it works, the pilot's attention is freed for higher-level judgment, whether to engage, whether to hold fire, whether to reposition, and how to contribute to the larger fight. Now add the layer that turns sensing into survivability: electronic warfare. Modern air defense is not just about missiles. It's about sensing and tracking. Electronic warfare shapes how you appear in the spectrum and how the enemy's sensors perform. It includes warning, geolocation, classification, jamming options, and countermeasure integration. The important point is that EW cannot be a separate pod strapped onto the side as an afterthought if you want it to work seamlessly in a high-threat environment. In the F-35 concept, EW is integrated into the aircraft's core, tied into the same fused picture that drives decision-making. And this is where the aircraft begins to behave like an information platform rather than a conventional shooter. It can sense threats, classify them, and share what it learns. Not everything, not raw fire hose data. The useful parts, tracks, identifications, threat cues, and the kind of situational awareness that changes what the rest of the force can do, that sharing creates the kill web effect. A kill web is not a single linear path from sensor to shooter. It's a set of connected nodes that can flex. A forward sensor can cue an offboard shooter. A ship can engage based on tracks it didn't generate itself. A ground unit can receive awareness it could never build from its own line-of-sight sensors. The value is that the force becomes more synchronized and faster at turning detection into coordinated action. This is why the F-35 is so often described as a force multiplier. Even when it is not the one firing, it can still be the one that changes the decision timeline for everyone else. It can operate closer to danger because of its survivability stack, build a cleaner picture because of fusion, and feed that picture into the team so others can engage from safer positions or with better timing. But this only works when networks are engineered realistically. Bandwidth isn't infinite. Spectrum conditions aren't friendly. Coalition interoperability isn't automatic. Data formats and confidence measures don't magically match. The system has to be designed to prioritize, filter, and route what matters to the nodes that can act on it. Otherwise, you don't get a kill web, you get a congested mess. The F-35's strong point is that it was built for this era. A fighter that assumes the fight is networked, assumes the spectrum is contested, and assumes decision speed is the real currency. The jet is designed to be a forward node that helps the force see, understand, and coordinate under pressure. That is why the F-35 is so strategically important. It doesn't just bring weapons to the fight, it brings clarity to the fight. And clarity, under modern threat conditions, is often the rarest commodity in the entire battle space. The ecosystem, weapons, upgrades, sustainment, and why it stays relevant. A modern fighter is not judged only by what it can do on day one, it is judged by what it can still do 10 and 20 years later, when the threat has adapted and the environment has changed. This is where the F-35 separates itself from many legacy aircraft. Not because it is perfect, but because it was designed as an evolving ecosystem, a platform whose capability is shaped by software, mission data, integration, and continual modernization. Start with weapons, because that's the point of any combat aircraft. The F-35's weapons philosophy is not simply carry more, it's carry the right effects in the right signature state. Internal carriage is the stealth configuration, weapons and fuel packaged inside the airframe to preserve lower observability and reduce drag. That configuration matters most early in a conflict, when defenses are dense and the cost of being tracked is high. But the aircraft is not locked into stealth purity. External carriage expands payload and flexibility. This is how the F-35 adapts to different threat environments and mission needs, trading signature for mass when it makes sense. The key is that the platform can shift between modes without turning into a different aircraft. That flexibility matters because real wars are not single mission stories. They are sequences. Opening penetration, suppression, strike, patrol, maritime support, persistent presence, and deterrence. The multi-role identity is central. The F-35 is built to operate as a strike platform, an intelligence collector, an air-to-air contributor, and a coordinator inside joint operations. In some contexts, it's a precision striker. In others, it's a forward sensor that enables other shooters. In others, it's a defensive counter-air asset that patrols, detects, and helps build a picture that makes the entire force safer. But capability is meaningless without readiness, and readiness is where modern fighters live or die. The F-35's sustainment story is not glamorous because it is not cinematic. It's maintainers, parts pipelines, diagnostic systems, and fleet management. It's how quickly faults are found, how accurately they are predicted, how efficiently components are replaced, and how consistently the aircraft returns to mission-capable status. In a real force, aircraft that can't generate sorties are not advanced. They are expensive hangar decorations. This is why digital sustainment and logistics systems matter so much. The F-35 environment is deeply data-driven. Fault logs, health monitoring, maintenance actions, configuration control, and the ongoing effort to reduce turnaround friction. When sustainment systems improve, sortie generation improves. When they lag, everything else suffers. Training hours, deployment tempo, and operational availability. Then there's the part that doesn't get enough attention outside professional circles. Mission data. A platform that relies on fusion and electronic awareness depends on updated libraries of the environment. Emitters, signatures, threat behaviors, and the patterns that define how an adversary's systems operate. Those libraries don't stay correct forever. Adversaries change waveforms, adjust tactics, introduce new systems, and modify old ones. If mission data falls behind, a fighter can remain physically capable but become informationally stale, which is a silent form of failure. Now add the modernization reality. The F-35 is software-defined. That means capability is not only a function of hardware, it's a function of processing baseline, code maturity, integration stability, and the pace of fielding. When modernization is smooth, the aircraft improves rapidly and keeps pace with changing threats. When modernization is delayed or uneven, fleets can split into different baselines, creating training complexity and capability mismatch across units.